here is an example of a thunderstorm system, looking at it on a grid resolution of 12 kilometers. Somewhere in the sort of middle of the time I was working in this area, we were able to push the line to the right. We had some bigger supercomputers that gave us more computing power, and so we could make our grid squares smaller. And then we could push that to 4 kilometers. And you can begin to see, we can start to get a bit more detailed information. At the point that I stopped really actively working in this area, we've managed to push this down to 1 kilometer. And you can begin to see the difference now of this trade-off you make with resolution and grid squares, and how that can affect the accuracy of what you're doing. If you look at the difference between the 1 kilometer and the 12 kilometer grid squares, then I think you can get a good appreciation of how much we managed to move the forecasting on. This isn't just, of course, by using big computers. That's part of the answer. But when you move from 12 kilometers to 1 kilometer, you also start to bring in a huge amount of new physics into the models. You've got to put a lot more cloud physics in there. Your dynamical systems have got to be much better. And you've got to be able to couple things that bring you right down into the lower turbulence scales. So lots and lots of physics went into achieving that move from 12 to 1 kilometers, not just big supercomputers. Now, the very first numerical weather prediction that was made for the public, there was lots of research models run probably from the mid-1950s. But it took 10 years before we got to a point that we're comfortable enough to make a forecast for the public. And the first of those was done by the Director General of the UK Met Office at the time, who's called Sir John Mason. Wrote a fascinating book on cloud physics. So if you're interested in looking at some fundamental cloud physics, B.J. Mason's book is a good place to start. And he did a very brave thing, you might say, which was he did the first forecast publicized on television, which could have gone terribly wrong, I guess. But here's John Mason in the press conference, and you can see the first weather forecast charts behind him. And luckily for him, it went well, I think. You might say it's all been downhill since there. Now, most of you will come across weather charts through the TV forecasts if you're not so familiar with them, or if you have more of an interest, you will perhaps for sailing or gliding or anything to do with the outside, you might look at these frontal charts. Frontal chart models were built starting really in the Scandinavian countries, where we gained to get those kind of early models of what a frontal system looked like in the sort of 30s to the 50s. And then we produced these frontal charts that look something like you see here. This is what we call an analysis field. And then we would use this analysis to move the forecast forward to create a forecast, a weather forecast. But before I talk a little bit more about forecasting, I want to show you how useful these analysis fields are, because they contain all of your best physics. They contain all of the latest observations we've got from the oceans, from aircraft, from radars, from satellites, from the ground-based observations. We bring all of those together in a large 4-dimensional variational analysis. So you've got the physics and the observations. It's your best understanding of what the current environment is at any one time. And so you've got a very powerful analysis tool, not only for forecasts. And let me give you a couple of examples of that. So here's a selection of just analysis fields. And this is going back looking historically at a significant weather event. And I'll just play it for you. The colors are rainfall. So the darker the blues, the heavier the rainfall. And the arrows are the wind's strength and direction. And if you locate the geography, this is New Orleans, and it's the Gulf of Mexico. So if you know your history of hurricanes, you will know this is Hurricane Katrina. Let me play it again for you so you can just watch it again this time with a focus a little bit on the dynamics of the system, which these analysis fields really help us to unlock. So you can see the hurricane coming in, category 4, as it passes over the Florida Peninsula. And watch when it hits the warm waters of the Gulf, you get a thump of energy from underneath, and then the system spins up and accelerates, and then you cross over the land, that heat source is cut off, and the whole hurricane dissipates. So you get a real sense of this moving as a fluid, and the way that energy helps to drive these systems. So these analysis fields can be really helpful in helping you understand the analytics of a system. Of course, the physics, as far as we know, works wherever we are in the universe, not just on Earth. So these models of atmospheric motion, you can run them for any planet you want, as long as you know a little bit about the surface of the planet and its atmosphere. And so here's a similar forecasting model we built for Mars, using the soundings from the Martian probes that were sent. And this is the south pole of Mars. And we ran this analysis field, looking at the different pressure patterns over the south pole of Mars to try and give us a clue on where the best places might be to send a Martian surface lander. So here again, it's running high and low pressure pattern models for the south pole of Mars. So you can run these anywhere. They don't need to be Earth. You just need to know about water, land, and atmospheric structures. So you can have great fun with these, playing around with the planetary sciences. And most of the planets in the solar system now have had the same models run as on those planetary systems. This was one of the first applications I ever made to the use of these analysis fields. And actually, it was one of the first times I ever had an interaction with the government policy process. We were looking at the time after what was called the nuclear accident model, the NAME model. And we had some alarms going off from the radiation sensors in Eastern Europe. And this was related to the Chernobyl event, where the power plant in Russia went into meltdown. And we had to then run the models and look at these analysis fields, because they can couple with the chemistry. So you can look at how the chemistry interacts with the weather, the meteorology. So you can look at how the fallout, the nuclear fallout, the cesium it was in this case we were tracking, can propagate with the weather, and where you might get deposition down to ground level. So here was our traces of the Chernobyl event. And you can see the Chernobyl plume spreading with the prevailing weather. It spreads out over Europe, circles over the UK, and then comes back over the UK from the south and from the west, and spreads south down through southern continental Europe. So I'll play that again so you can just watch this. So this is us using these analysis fields to move the plume and to track the dispersion of the plume. And it was on the basis of these models that we were able to share this across Europe and think about measures we might put in place to reduce the surface contamination, moving into things like the food chain and the biosphere. So these can be very powerful tools in their own right. But of course, the main principal development for them is to use them for weather forecasting, principally for the protection of life and property and the production of severe weather forecasts. That's really where the drive for weather forecasts first came from. Let me come down in scale a little bit now to the size of thunderstorms. I spent a lot of my research time working on the dynamics and convection and turbulence within thunderstorms. And here's a picture taken from a radar based in the UK and it's pointing out in the vertical and taking a sort of vertical slice through the sky. So the radar based here on the left-hand side, pointing out towards the right, taking this vertical slice through the weather. And you can see straight away that the majority of thunderstorms are not just one single convective cell. They're a multiple collection of these convective cells all gathered together in what's called a multi-cell system. And you can see these individual vertical columns of convection gathered together and feeding off each other almost like a living system. And here in these darker colors is where you see the heaviest rains, is the core of these convective cells. But if you look carefully, where you can see the heat pushing up through these cells, you can see the convection rising up towards the tropopause and then hitting the tropopause and spreading out in these as the convection bursts through the top of the cloud. And of course, the stronger the convection you can set up, the more stronger the thunderstorm. I'm going to play you a little bit here of a choir trying to reproduce the sound of a thunderstorm. I hope my microphone picks it up for you. I'll try and turn the volume up if not. So I hope the audio worked on that. Hope you recognize that kind of rainfall pattern that you can sometimes hear from me sitting listening to rainfall. And it's remarkably good at representing the life cycle of a thunderstorm. They did a terrific job. If you look at the development of a typical convective cell sitting within one of these multi-cell thunderstorms, then the life cycle of that cell is about 30 minutes or so, and together these individual cells create thunderstorms which will last, roughly speaking, about 60 minutes, and they go through exactly that life cycle as you've just heard. They start with the development of the convection, then about 20 minutes or so into that you'll begin to see the rainfall. The really heaviest period that we see from the convection, which is the really heavy rainfall, and if it's very intense, the thunder, lightning, and maybe even sometimes hail, which I'll say a little bit more about in a moment. And then you get this long tail of dissipation over the next 20 or 30 minutes. So the key to doing any forecasting of thunderstorms is to try and represent this life cycle model in the numerical models. And that means having to have all of the cloud physics in there, everything that's going on with the water and the ice in the top of these clouds, and how that water and ice and energy is all interacting. So these cloud physics models can be quite complicated. And I've tried to sort of represent stylistically what's going on in one of these cells, and I'll try and explain that a little bit and unpick this diagram for you. Which doesn't do justice in 2 dimensions because it's a very 3-dimensional process that's going on. So you have something that's either heating the ground, so solar heating of the ground, or the air might be hitting a hill and causing it to rise. So anything that will cause the air to lift by heating it or moving it over the land surface. And so if the air is warm enough and buoyant enough, it will rise up into the cloud where it cools and it sinks again. And that's how this convective process starts, of the warm air rising and the cold air sinking. To get the thunderstorms to establish themselves, you have to have some wind shear in these upper levels of the atmosphere, because if the air going up and the air coming down are not shifted slightly, then the air coming down will chop off the air coming in, and it'll just cut off the air supply for the thunderstorm. Because as the cold air comes down and spreads out, it will cut off the inflow. So you need some wind shear to twist the air a little bit, so you can keep the airflow coming into the cloud as the cold air comes out. Now the cold air comes out and spreads out, forms this very cold pool underneath the front of the thunderstorm. And you may have felt that if you're out in the garden or out in a park somewhere, and you feel that cool breeze first, then you know from the life cycle you've got about 10 or 15 minutes and the rain is coming behind it. So there's a good predictor for your friends when you're out and about. Of course, this cold air spreading out can meet warm air in other regions and create a new convective cell, what we call a daughter cell. And that's how you get these separate convection cells being formed, and how you develop this multi-cell structure, and how this multi-cell structure keeps itself going, keeps propagating by the birth of these daughter cells. And let me give you an example here. If you look in the southeast here, you'll see these darker areas are thunderstorms. This is rainfall. And if you watch in the southeast, you'll see some of these daughter cells being born. And the pinks and the reds and the greys, the really heavy rainfall areas. And you can see a daughter cell just born in the southeast here. And then another daughter cell born again right in the south of the picture. So these multi-cell systems can keep themselves going as they propagate on. And there is a preferential direction for this. Usually you will see as the storm moves forward, these daughter cells will develop to the lower left of the main cell. So again, that gives you some clues when you're developing your forecast models. So let me go back briefly to the life cycle. So if we know the life cycle structure, and we have satellite and radar pictures, like the one I've just shown was a surface radar picture, telling you what the different rainfall intensities are at any one time, you can put the actual data together with the conceptual model that we've got and the physics, and you can create a forecast system. And this is where we managed to get to probably about the mid-90s. I'll show you a little bit at the end about where we got to in present day, but this is where we were. So this is an example from 1994, but for about 2 or 3 years before that, we were beginning to experiment with these ideas of combining the life cycle model with the data. So once you've done this is another analysis field. Then all you have to do to roll this on is every square that's early mature, you move it on to be a late mature, and then every late mature to be an early dissipating. And so this begins to give you 10-minute forecasts, or what got colloquially called nowcasts. And these are very important for people who are working in things like flash flood warnings, where you need very short timescale warnings, or people who are working on electricity lines, or trying to prevent damage from hail. Is that if you can give at least half an hour warning, then you can begin to create something that's useful. And of course, in the very, very intense thunderstorms, where the wind shear is very strong and the temperature gradients are very high, you can get really intense hail, very strong lightning, and of course, tornadoes. I'll say a little bit about the development of tornadoes in a moment. Let me talk about ice first, because I think ice is and hailstones particularly, a really fascinating part of heavy thunderstorms. And I hope it shows up in the picture here. You can see, hopefully, these darker, fainter rings like tree rings coming out from the center of this, this hailstorm. And these are layers of water that have been frozen onto the ice. So as the water rises in the hailstorm, thunderstorm, it goes up to the top of the cloud where temperatures can get down to as cold as -40. So the water freezes and forms these ice pellets. These pellets fall down through the downdraft, but then hit the upcoming air again. And if the upcoming air is stronger, it pushes the ice pellets back up into the cloud. The water that's on the surface on that freezes again, and then they fall down again and then lifted up in the updraft again. Another layer of ice is frozen onto them. So you build up the hailstone through depositing these layers of ice onto, and then eventually the hailstone just becomes too strong for the updraft and falls out of the thunderstorm. So literally, and you can try this if you're quick enough, because you do have to be very quick. If you get a hailstone and just cut through it across the cross section, you can count how many times the hailstone has been traveled through the thunderstorm by just counting the rings within it. And it tells you a little bit about its life cycle, which I think is fascinating. And these can get very big in the very intense thunderstorms. They can get very big. I've seen in Canada softball size hail. The largest one was measured in a thunderstorm in Bangladesh, and it weighed a kilogram, I should say, in weight. So you can imagine a kilogram hailstone. Thankfully, the very big hailstones are quite soft in nature. The ones you get real danger for are the ones that are about golf ball size, because they keep their very hard structure and they can do an awful lot of damage. Lightning, of course, is always a common thing you see in thunderstorms, hence the name. And in fact, the symbol for thunderstorms on the meteorological observers symbols that we use on the maps has a little jagged line for lightning. What's happening, how the charge is being generated in the cloud is, as the convective cloud grows, the top and the bottom of the cloud separate, and the charge is distributed traveling on the surface of the water and ice via electrostatics. So as the cloud spreads out, you're able to create this greater and greater charge separation, with the positive charge going to the top of the cloud and the negative charge in the base of the cloud. And that induces a local positive charge on the ground. So you've got this positive, negative, positive charge separation. The air in the cloud is pretty good at creating some resistance. And so it allows the charge to separate, and you get this voltage potential being built up. Eventually, the air can't hold that any longer, and you get the breakdown of that voltage, and that's discharged through these lightning strikes. You get about 30,000 amps in one of these just on average in one of these lightning strikes. You can see from this picture there's a fairly jagged nature to the lightning strike, and you've probably seen that yourself when you've seen strikes in the sky. And the reason for that is obviously the charge is trying to find its way from the cloud to the ground in the fastest way possible. So it's moving down, creating a channel as it goes through the air. And each time the channel darts, it's because it's found an area of path of least resistance. So it's darting down the areas of least resistance as it travels. And that channel heats to about 30,000 Kelvin in a fraction of a second. And so the air in the channel expands very quickly. And that's what you hear as the thunder. And you'll often see a flash through the same channel. So once the channel is established, several discharges will happen down through the same channel. And that's what creates the flicker in the lightning. The reason I showed this picture is because you can see there looks like a lightning discharge coming up from the ground, oddly. And a lot of people have this idea of the lightning coming from the ground, coming from the cloud, striking directly the ground. More often than not, because of the induced charge below, you have what's called a leader will come up from the surface to connect with the channel as it comes down from the cloud. And the connection often forms higher up in the atmosphere, and then the discharge through that channel. And the old adage is true. I don't know if you've ever done this. If you've counted the seconds between the thunder and lightning, you will know very well that with the speed of sound and the speed of light being different, that does tell you a little bit about how far away the thunderstorm is. So about a mile for every 5 seconds you can count. Tornadoes, of course, are one of the most powerful features we see that coming out of thunderstorms, what we call supercell storms. And you see these are in most countries have enough temperature gradient between the warm and the cold air to produce tornadoes. Quite a lot that happens on the boundaries between land and water. So often, particularly in coastal countries, and like the UK, the most prominent place you'll find tornadoes are actually over the water, just off the coast. And you can see that in the south coast of the UK. They're called water spouts when they occur over water. It's where you get very strong gradients of temperature between the warm and the cold air. So predominantly, although we see them in many countries, Midwest America sees these quite a lot. And we have the very famous Tornado Alley in the US. And that's because you've got the very warm air coming up from the Gulf of Mexico and the very cold air coming down from the Rockies where they meet. The tornado is a symptom of the air that's sitting within the storm trying to equalize very quickly. So you've got the characteristics of some air up above and some air on the surface, and they're trying to equalize, and they have to pass each other. And one of the most efficient ways to pass each other is to move around each other. So the air does this as it exchanges in the vertical. And that's why you see this rotating motion. And we sometimes do this with the youngsters in schools. We have the demo with the 2 bottles and the water, and we swirl it around. And what you're doing is you're exchanging the water in the top and the air in the bottom in the most efficient way around each other. And of course, you see that every day as you let water out of your sink. The air inside these tornadoes is moving incredibly fast, so about 300 miles an hour, and so fast that the pressure inside that funnel drops incredibly low, and so the moisture in the air condenses out of the air because the pressure has dropped so low. It cools the air, forces the air to condense, and so you see this cloud forms, what they call a funnel cloud. So that's showing you the area of fastest exchange and the most intense pressure difference. And of course, this looks a very narrow tornado. It's very iconic sort of tornado shape. But in practice, tornadoes are much broader than that and can cover much bigger areas. And often they're actually hidden in rain clouds. So you don't get a clear view as you do in this picture. And that can be a real challenge for predicting and for issuing warnings. So developing these early warning systems, these nowcasting systems I spoke about, looking particularly at the characteristic signatures and areas where the tornadoes might form, is a really important part of forecasting research. I showed you in the mid-90s where we got to. A more present day, this is the kind of model we have now. So we've abandoned these conceptual models and instead we use these models here of, let me restart the picture. We use these animations using very high resolution numerical weather prediction models. This is only about 100 meters or so is the grid length of this model. And all the cloud physics that's sitting in here that's telling us about the different rotations of the air as it moves around and where we would expect to see the heavier rainfall, potential hail, lightning. So we're moving forward at a pace in terms of the development of the technology. I want to say a little bit about the communication of forecasts, because you can produce as many good forecasts as you want, but if you can't get that information over to the public, then it's not much use, particularly if it's in terms of warnings. And this is kind of my most favorite one, I have to say. This is a toaster that where you dial up the weather forecast in the morning and it burns the weather forecast onto your toast. That's definitely a good thing to put in the present list for Christmas. But most of the time when you're forecasting the weather, you're dealing with issues of uncertainty, and trying to communicate uncertainty is a challenge. This is something that's called a postage stamp diagram, for perhaps obvious reasons. Each one of these squares is a model run, a weather forecasting model for the globe, like the general circulation picture I showed you at the beginning. But instead of just running it once and getting one of these squares, we've run it many times by changing the initial start conditions of our model a little bit to try and cope for the fact that our initial conditions might have been a little bit inaccurate. So I move the start position a little bit, run it again, move the start position a little bit, run it again. And I can create this, what's called ensemble of forecasts. And then the way you build up the probability forecast from this is let's say we wanted to find the temperature of what's happening over a PLANCKS conference, say in London. Then I just find the little grid square that's sitting over London, and I pick one of these forecasts and I get a temperature. And that's what you would get if you were doing just a standard weather forecast, where you just run the model one time. But with more powerful computers now and our ability to run this many times and create this ensemble, I can pick another one of my ensemble and look at the grid square and read off that temperature, and I can do the same. And I can begin to build up a distribution of temperatures. And suddenly you can see that in my very deterministic model that I ran the first time, I can get a single temperature, but now I've got a much richer picture of the likely distribution of temperatures. So I've got a mean, so I've got the most likely, and I've got a distribution of temperature being warmer or colder than that mean. So suddenly I've got a lot of information that I can give to people about the accuracy of the forecast and how much uncertainty is sitting within the forecast. We first began to build these models really for those where the uncertainty mattered a lot. So that was in retail shopping, in oil and gas forecasting, where you're trying to predict the likely future of use of energy by households or businesses. And we created these maps. So this is my distribution that you saw on my previous slide, but this time moving out in time. So just creating a time series of all these distributions. So I've still got my mean, I've still got my probability to be warmer and my probability to be colder. And this was the very first one of these charts we produced. And I have to say, it surprised us enormously. And I don't know whether it surprises you, or if there's anything you particularly spot from this that we spent a lot of time pondering. And that is that the accuracy of the forecast doesn't decrease as you go out in time. Logically, you'll think the longer the time the forecast is made for, the less accurate it will become. But here you can see in this chart, there are regions where the distribution of the probabilities are much wider, and there are probabilities where the chart is much narrower. And that doesn't go out linearly. And the reason for that is because the atmosphere can get itself into different modes of predictability. So sometimes it can be more easy to predict than others where it's behaving more chaotically. And interestingly, that means that it's the quality and predictability of the atmosphere is not simply a function of time, which is a very interesting thing for weather forecasting, I think. We played around a little bit with showing different ways of getting this uncertainty across to the public. And we tried to do it in words. So here's an example of my probability distribution with the most likely in bigger and bold letters and then fainter as you go out. Here it is in pictures. We tried to do it in percentages, and we did it as sort of error bars. And we did a random survey of 1,000 people. and interestingly, we had an almost equal number. There was about 250 or so voting for each one of these. So it was a four-way tie for the way that the people preferred the information to receive that probability information. And I think that told us one thing, that there's no one way to communicate this, and people understand kind of probabilities and uncertainties in different ways. And you'll see that now in a lot of weather forecasts, is they don't particularly use any method of showing uncertainty. They will use a combination of pictures and words, and they'll change that around a bit. And the reason for that is to try and to get this over in different ways to different people. Let me finish on a few words about climate and climate modeling, because towards the beginnings of 2000s and 2000, between 2000 and 2010, there was a lot of work going on in the development of international policy around climate, of which we're still seeing the follow-on of those discussions today. A lot of work about how we use the science to inform those policymakers, both across the science community and in the political community. So go back to my first picture where I came into this. You can see this is pictorially what the Earth's climate systems looks like, with the solar radiation coming in on shortwave, and then the long wave radiation going out, and the Earth trying to balance that, and the climate being the kind of statistics of that, of how that's being done. Let me show you it in a slightly different way. This is looking at it, looking at the radiative transfer, that in a bit more detail of what you're seeing in those pictures. So if we do the theoretical calculations of what's coming in, then you see that should be the red line here, and then what's going out should be this middle blue line. But what we observe in the pictures that I've just showed you with the solid red areas and the solid blue areas. So why don't we observe what we see in theory? Well, the answer is, of course, the greenhouse gases in the atmosphere. If I look at the incoming radiation, you can see here that these gaps on the right-hand side of the incoming radiation, why aren't we seeing the theoretical values, is because the water vapor is absorbing some of this incoming radiation. And again, in the outgoing, only 30% is getting out the atmosphere. The other 70% is being absorbed by the water vapor, the carbon dioxide, the methane, and the other greenhouse gases in the atmosphere. That's causing the atmosphere to warm. And of course, one of the signals we look at to confirm that is not just that the atmosphere, the troposphere is warming, but the stratosphere therefore must be cooling, because much less of that heat is getting out into the upper atmosphere. If I show you that mathematically, here's a very simple climate model. So you've got the solar radiation coming in over an area, my pi r squared, and you've got the albedo, that's the amount that's reflected by the ice and the clouds that I mentioned. So you've got what's coming in times what's the reflection coefficient is equal to what's going out. That's the emissivity, how good a body is at emitting that temperature over your spherical area. And then this is just the Stefan-Boltzmann constant. So what's coming in, it has to balance with what's going out. So here's a very simple climate model. So you can see that really it's just depending on those three things: the albedo, the emissivity, and what's coming in from the solar side. And you can get some very good estimates of temperature using that. And in fact, ironically, this was one of the things that we we struggled with in the early days of trying to encourage government to invest in climate modeling and to buy the big supercomputers we needed and to invest in the climate science. Because using this very simple model that I've just shown you, you can see that if you double carbon dioxide, you'll get a 1 degree rise in temperature, and you'll get another 2 degrees rise because of the water vapor feedback. The warmer air holding more water vapor, creating additional rise in temperature. So double carbon dioxide, you get a 3 degrees warming. And you can do that from that simple model I just showed you with some school level physics, really. So why do it? Why buy big climate models? Why invest in national climate programs? Well, the answer is, of course, it's the feedbacks that we have to worry about. The hard work that the computer models do and the Earth simulation, Earth system models do, is to look at this feedback that's coming from the changes to the ice and clouds and snow and what's happening in the oceans. So it's those feedback processes which are much bigger than the forcing terms. They are the things that really we use the climate models to tell us about. In the very early days of the climate models, we had to convince ourselves that we understood the processes that were going on in the models. And a good way to do that is to see if you point the climate models backwards to see if we can reproduce historical climate. And these are some of the first pictures that we produced doing that. So these black lines are the observed temperatures. The blue line is the climate model prediction. And the faint blue lines is my ensemble that I spoke about earlier to try and capture the uncertainty. So this is the ensembles of different climate model runs, and this is my mean. And this is a run without any human anthropogenic greenhouse gases. So this is just naturally occurring climate. And you can see on here, we've put the very largest volcanic eruptions, the eruptions that put a lot of particulates very high up into the atmosphere. And they can cool the planet for very prolonged periods. So you can see the eruption of El Chichon and the eruption of Pinatubo. They cooled the planet for 3 or 4 years, quite significantly. And then we added the human greenhouse gases into the model. And you can see we can much more closely represent the observed climate, not completely. There are areas around here in the 40s that are still, we're not really accurately representing. But this gave us some confidence that the physics that we had in the models was really representing the climate processes that were going on, both in the atmosphere and in the oceans. So we used some of this early data, these early models that we tested this on, to do some of the very early predictions that were in the first assessment reports. There was a lot of discussion in the IPCC in the early days when we were trying to form these global policies like the Kyoto Protocol, that it really should be the job of those who emitted the most carbon dioxide or the most greenhouse gases. And here is a list of the top 10 global emitters by percentage of emission. And I've grouped Europe together as one block. And there was a lot of focus on Europe, the US and China. But we showed this in one of those early meetings. So we recast the graph by per capita, by per head of population. And you can very quickly see that the picture looks very different if you include the population size. And it's not surprising in places like Canada, where it's very cold and you need to burn a lot of fossil fuels to heat places, then the per capita emissions are going to be very high. Or in countries where you've got a lot of industrialization, a lot of people working in industrial economies. So it's not at all as straightforward as saying those who emit the most should be the ones who those reduce the most. It's a more complicated picture than that. And this sparked a really interesting discussion, I think, about mitigation strategies globally. A little bit old now, but there's a really fascinating book by someone called Mike Hume, who talked a lot about why we disagree about climate change, at least finding solutions to it. And Mike talked about the fact that, sometimes that's because we take an economic view. We might take a technology view, that we will innovate out of this, or we might think it's due to overconsumption because of population, or it might be driven by a global injustice argument, or maybe even that it's just natural, and there may be a belief this is just all caused by natural variability, or that the climate has significant tipping points and we have to do dramatic things like geoengineer the future. Mike's point was that we come at this from very different perspectives, or what he called very different frames of references. So unlike the ozone hole and the Montreal Protocol, where we were able to find a very simple technical solution that was already available, climate isn't like that, and people and countries come at this from very different perspectives. So I just close with one last slide to provoke perhaps a little bit of thought on this, as we all talk a lot about the green economy and net zero carbon. If you have an emissions curve where you want to get from a high emission to a low emission, then of course you've got to set yourselves targets, and government is very good at setting targets, but we must remember that it's not just the targets, it's the journey along the way towards the targets that matters. Because if you don't start making progress along those journeys towards the targets early on, you leave yourselves a lot to do later down the line. And the challenging thing for a lot of these climate agreements is a lot of the things that help us start to make progress along these journeys are technologies and solutions that are some way down the line, whether you think that's more nuclear power, bigger scale renewables, carbon capture and storage. All those big technology things take time to bring online. And the things that we can, the handles that we've got to pull at the moment, and the only way we can address these things now are a bit more about how we use energy and energy demand. And those are about the behaviors of all of us. And that's why I think making progress more quickly down the early part of this curve remains a challenge for many countries and certainly many individuals. I better bring that to a close, as I'm sure I've talked for longer than I should have, but Molly, I'll hand back to you. Thanks.
Great, thank you. That was a really interesting talk and a great way to close off the weekend before the results. We have time for just one question. So from the chat, have you investigated ball lightning? What is your opinion on this phenomenon?
Yeah, ball lightning is fascinating. So for those who don't know about ball lightning, that's lightning that appears in a football shape, usually about football, basketball size, but it can be up to 2 meters across. And it's very low in the surface often when it's seen, and it travels very quickly in horizontal lines. There has been reports of ball lightning forming inside aircraft and traveling down the aisle of an aircraft, which I'm not sure I really want to observe. For a long time, people said ball lightning wasn't possible. It couldn't theoretically exist. So we thought it must be people seeing things, imagining particular things. But of course, with mobile phones, we've now been able to capture images of ball lightning happening. And it's where you've just got this induced current along the surface, often above surface laid or low-level power lines, where you can get the lightning being induced in between the power line and the surface and traveling very quickly. And it's hugely dangerous. It's positively charged, often very dangerous, very destructive. If you see it, you don't want to be anywhere near it, that's for sure.
Yeah. Great, thank you so much. And once again, thank you for joining us today. I will pass back to Julian, who will go on to the next segment today.